Hi, here we have an inclined plane problem. And we have, so basically an inclined plane is just a ramp, okay? So we have a 5 kilogram box that's at rest on a ramp at a 30-degree angle. We want to know what's the normal force, what is the frictional force, and what is the coefficient of friction. So first thing we want to do is draw a free body diagram. So we have a box, it's on a ramp, and we have force of gravity pulling down on it, going straight down from the center. I'll also just label that as weight. And then I have the normal force, which is going perpendicular to the ramp, to the inclined plane. And then since it's at rest on a ramp, what's preventing it from going down the ramp is friction. And friction, so that means that friction is going up the ramp. So that's going to be my frictional force going up the ramp. Now, here's what makes this a little bit tricky with inclined planes, okay? You can see we have three vectors. These two are perpendicular to each other, but this one is kind of in between. So that means we have to break this up into components, okay? So since these two are kind of on the same plane, we're going to go ahead and break up the weight into components, at least on the same plane as the normal force and the frictional force, okay? So we're going to break up the weight into components, okay? And you can see right here I have a right triangle. I forgot to label this my angle. This is 30 degrees, okay? Now, this right triangle, this one side up here, make a little arrow here, this is going to be my 30-degree angle, okay? Um, Now, to label these, this is going to be my weight parallel and my weight perpendicular. Where I'm coming up with those is that this weight, this is the component of the weight that's going parallel with the ramp. This is the component of the weight that's going down the ramp. Okay, and this other weight perpendicular, this is the weight that's perpendicular to the ramp. Okay, so this is the weight that's going downward, well, not really downward, but perpendicular to the ramp. Okay, so I can redraw this down here since it's got a little bit messy up there. So let me draw this my weight. There's my right triangle. This is my weight perpendicular, and this is my weight parallel, and this is my 30-degree angle. Okay, so I am solving for normal force. Now, what's also key with this is that it's at rest. So that means that acceleration is equal to 0, which means that from Newton's first and second law that the forces are balanced. Okay, so all of these forces are balanced because there's no acceleration up and down the ramp. There is no acceleration perpendicular to the ramp either. Okay, so that means that these pairs of forces are balanced with each other. So that means that we are going to have relationships here with frictional force, which is going up the ramp, and the force that's going down the ramp, opposite direction but equal in magnitude, is my weight parallel. Now, it's the same thing with my normal force. My normal force is going perpendicular to the ramp upward, while my weight perpendicular is opposite in direction but equal in magnitude because, the acceleration is 0, so forces are balanced. So this is my weight perpendicular. So, when they're asking us to solve for normal force and frictional force, they're really asking us to solve for weight parallel and weight perpendicular. Okay, so they do give us a mass of 5 kilograms, and since we're solving for the components of weight, we do have to solve for weight itself first. Let me just do that really quickly here. So weight is equal to mass times gravity. Mass is 5 kilograms times gravity of 9.81 meters per second squared. And so my weight ends up being 49.05 newtons. Okay, so there's my weight. So now looking at this triangle, okay, this is just basic trigonometry now. All right. So since we want to solve for normal force first, we really want to solve for weight perpendicular. I know the weight. The weight is my hypotenuse, and the weight perpendicular is adjacent to this angle of 30 degrees. So that means adjacent hypotenuse, I am going to use cosine. So cosine of 30 degrees is equal to adjacent, which is my weight perpendicular, over my hypotenuse, which is my weight. So really, to solve for weight perpendicular, it is really just cosine of the theta, which is 30 degrees in this case, times the weight. So let me go and just plug this all in here. So cosine of theta is cosine of 30 degrees times the weight, which is my 49.05 newtons. And so for my weight perpendicular, I get 42.5 newtons. Okay? So, now we're going to do the same thing for the weight parallel. The weight parallel is opposite of the 30-degree angle. I know the hypotenuse, which is my magnitude of the weight. So again, it's opposite and hypotenuse, so it's going to be sine of 30 degrees is equal to weight parallel over weight. So again, to solve for weight parallel, I'm going to multiply both sides by the weight. So I end up with sine of theta, theta. There we go. Sine of theta times weight. Okay, so now I can just kind of plug in my numbers here. So weight parallel is equal to sine of 30 degrees times the weight, which is my 49.05 newtons. Okay, so now to solve for weight parallel, sine of 30 is 1/2 times 49.05, and I get 24.5 newtons. So I've solved for weight perpendicular, I've solved for weight parallel, so that really means that I solved for, from looking at this relationship up here, I've actually solved for my normal force because the forces are balanced. So again, what's really key in this is that it's at rest. Okay, so now same thing with weight parallel. That's equal to my frictional force. So this is also my frictional force. We have one last thing to solve for, and that is the coefficient of friction. So coefficient of friction, the only real equation we have with that is frictional force is equal to mu times the normal force. Now this is static friction, okay, because it's at rest. So I'm really solving for coefficient of friction for static. So now frictional force I said was 24.5 newtons. That's equal to mu times the normal force, which I said was 42.5 newtons. Okay, so my mu, once I do the simple algebra here, divide both sides by 42.5, I get mu of 0.576. Okay, so we solve for the normal force, which was just equal to the weight perpendicular because it's not accelerating perpendicular to the ramp. I solve for the frictional force, which was really just my weight parallel because it's not accelerating up or down the ramp at all. And then I also solve for coefficient of friction. Okay, so that is your first inclined plane problem.